Okay, we will look at explain 2 now, which is growth patterns in context. So these are real world type of scenarios. So our example 2 follows a bungee jumper jumping off of a bridge. If you've seen this before, you notice after the first jump, they come flying back up and then they go back down. The second time, they don't come back as high. Third time, they don't come back as high. Eventually, they just start settling down until they stop. This follows a geometric sequence as far as how much they bounce each time. So what we can do, we can find the height at the top of the 5th bounce. So if the first 3 bounces, we have first bounce is 200 feet, they bounce back. The second bounce, they bounce up 80. Third bounce is 32. We first find our common ratio, 80 divided by 200. It's 0.4. All right, we can know our first term is 200. Our second term is 80. We can write that as 200 times 0.4, or 200 times 0.4 to the first power. All right, remember that from our exponents last week. Now, our third term, 32, we can think about that as 80 times 0.4, which is the same as 80 times 0.4, or which is the same as 200 times 0.4, which is 80 times 0.4 again. So our third term is the same as 200 times 0.4 squared. All right. Eventually, we're going to get to a formula that we'll use from this, but as we're going, we multiply it by the common ratio to the n minus 1 power. So, however many bounces we want, since we're looking at the 5th bounce, we start with 200 times 0.4 to the 5 minus 1 power, or 0.4 to the 4th power. All right, so we can calculate that or we can use our calculator for that to find that a little bit faster as we go, especially if we're dealing with higher number of terms. So it starts with our first term, times our common ratio to the n minus 1 power. Okay, example 2. If we're looking at a ball bouncing, if it starts off, it drops from 144 inches. On the first bounce, it's 72 inches. All right, make a note of that. 72 inches, that's our first term. How much it bounced back. Okay, so term 1, 72. Our second term, the next time on the second bounce, it's 36 inches. So term 2 is 36. And term 3 is 18. All right, so we got a quick table. We want to find out what it would bounce to on the 6th bounce. So starting with this, we're going to look at finding our R value. Take the second term, divide it by the first term. 36 divided by 72. Our common ratio is 1/2. All right, our first term is 72. Our second term is 36. That's the same as 72 times 0.5, or 72 times 0.5 to the first power. All right, f of 3, 18. That's the same as 36 times 0.5, our previous term times 0.5, or 72 times 0.5 times 0.5. All right, which would be 0.5 squared. Okay? So, in each case, we're multiplying 72 by the common ratio. Okay. So in each case, to get f of n, we multiply 72 by the common ratio of 0.5, and we're multiplying it n minus 1 times. Okay, so when n was 2 for the second term, we multiplied it by 0.5 to the n minus 1, which was 2 minus 1, or the first power. So we multiply 72 by 0.5 to the n minus 1 power. All right? So the height of the ball in the sixth bounce is f of 6. So n is 6. We multiply that by 0.5 to the 6 minus 1, or to the fifth power. And let me bring up a calculator here. All right, 0.5 to the fifth power is 0.03125. So we multiply that by 72, and we get 2.25. So after the sixth bounce, it's going to go up 2.25 inches, or 2.3 since it said to the nearest tenth. All right. So on this reflect, is it possible for a sequence that describes the bouncing height of a ball to have a common ratio greater than 1? In order for it to have a common ratio greater than 1, each bounce would have to be higher than the one before that. So the answer to this one probably is no. All right. Your turn. Start with a dropped ball. Okay. So we want to find the height of the bounce on the fourth bounce. We know the first bounce was 6, the second was 4.5, so we find our common ratio R. R is going to be 4.5 over 6. That gives us a common ratio of 0.75. Okay, 0.75. Now, if we can find the fourth term one of two ways here. We can take 3.375 and multiply it by our common ratio of 0.75, and that'll give us the answer. Or, since we're looking for the fourth term, we can take our first term, which is 6, times 0.75 to the n, which is 4, minus 1. So 4 minus 1 is 3. So 0.75 to the third power. All right. And on your calculator, either way to do that, 6 times 0.75 to the third power is 2.53. All right, so our fourth term is 2.53. We can check that, see that it works both ways. If we use our 3.375 times 0.75, it does give us the same answer. So either way does work. All right. For the assignment for this section, page 675 through 677, 11, 13, 15, 16, 18, 19, and 20. Again, I will make a homework help video that'll go through a couple things to prepare you for that.